This is just a list of some common acids, and some of them you are probably familiar with, like acetic acid. I mentioned it already. It's vinegar, carbonic acid, nitric acid, sulfuric acid, and hydrochloric acid are three of the big major strong ones. There's also HClO4. That's the perchlorate or perchloric acid. This is also a strong one. Those are the four major strong ones that you probably need to know. Everything else is going to be either moderate or weak. And if it's moderate or weak, you have equilibrium constants, right? Because you'll have products and reactants present. You'll have phosphoric acid, for example, present, as well as the conjugate base and the hydronium ion will be present, all three of them in considerable amounts, and so you can set up an equilibrium constant, as you know from chapter 15. And so this one is actually interesting. It's a polyprotic acid. It has 3 acidic protons, and they each come off in separate steps, right? So the first equilibrium constant is actually pretty high comparatively. It's not strong, so it's smaller than 1. So we have H3PO4 aqueous, which means the majority of what's present in solution is the solvent, which is water. So the reactant, since the reactant is water and has the little L here, we don't count it, or we don't use it at all in the equilibrium constant, because it's there as an excess, and only a small portion of the solvent will actually react with the phosphoric acid. So it does not become part of the equilibrium expression. But what it forms is H2PO4, which now has a negative charge. It's the conjugate base, as we know already. That's aqueous. And then the hydronium ion, which is the result of the reaction with the base. Now that's aqueous, and so this has an equilibrium constant Ka, A as in acid, just to specify. And we also call this, because it's a polyprotic acid, meaning it has more than 1 proton to donate. In fact, there are 3, as I said, so this would be Ka1. And we can set up that expression just like we did by putting the concentrations of the products over the concentration of the reactants. So the dihydrogen phosphate concentration times the hydronium ion concentration all over the phosphoric acid concentration. And we're not including the liquid water. Remember, solids and liquids are not included because they're there in excess. We also understand what we just learned in the previous lectures, that the conjugate base, H2PO4, can react with water, and where now water is going to act as a base. Again, it's important that this is liquid, and the result then would be phosphoric acid, H3PO4, aqueous, and hydroxide ion. So this would have a, let's say, a Kb, right? Okay, that's a base. So this would have a Kb, and we can write the expression for Kb, which is equal to the products, concentration of the products, which is in molarity, capital M, PO4, times the concentration of hydroxide, divided by the concentration of the dihydrogen phosphate ion, but not the water. So this is Ka1 and Kb, so this is really easy for us. Just pay attention to the little liquids and the solids. Looking at the second proton here, right? So you can also have the dihydrogen phosphate act as an acid, right? And so then it will produce hydrogen phosphate. That would be the conjugate base and an acid. And then it can actually do this in a third step where HPO4 donates the third proton. So, but then the equilibrium constant gets smaller and smaller, which means we have here for the first Ka here, this is the Ka1, 7.5 times 10 to the minus 3, so that's pretty small. That means we probably have more than 90% of it is present as this, and then 10% of this breaks apart. And then of the 10%, even less distributes or is dissociated in this step here. So we have even less of this present here, 10 to the minus 8. And then the third one is actually 10 to the minus 13. So there's a very, very, very little of these other species presence. But the main point here is that you are able to write this expression based on an acid-base reaction. So this goes back to chapter 15. And you do understand what this value here means. The magnitude of that is important. And this is a new relationship that will come back. Okay, there's something called the Kw, which is the water dissociation. I'll tell you what, I'll come back to that on a separate slide. Let's move on for now. So this is a table of weak acids, and so you will be provided with that table, and so these Kas here, you should be able to look at that number and distinguish how strong these acids are, right? So the smaller the equilibrium constant, the weaker the acid here, right? So these are listed from strongest to weakest, and it tells you, I told you you wouldn't have to worry about how many hydrogens can come off here, right? Like this one has tons of hydrogens. It's just the one, like benzoic acid, and even if it was a polyprotic acid, you would still be able to, it's only the one that comes off, and each step has its own equilibrium constant. Then there's something called the pKa that's also important. So that's just the negative log of something. In this case, it's the negative log of the Ka, right? And so you see how the pKa here increases the smaller the Ka is. Okay, what that can tell you is how strong, relatively strong, the conjugate base is here, right? Because each one of those produces a conjugate base, right? Fluoride, and all of those are conjugate bases, and they can react with water to form the acid back. And so if the pKa is large, or if the Ka of the acid is very small, then that means that that's going to be a relatively strong base, because it's going to have the tendency to react back to form once you have some of the conjugate, like the acetate. If you have acetate in solution, most of that is going to react with water to form the acid back. That's benzoic acid, not acetic acid, but it's irrelevant. So, okay, so let's take a look at that relationship between hydronium and hydroxide. So the Kw that I was referring to a minute ago on another slide, right? So we do know that water can act as an acid or a base, and it receives the proton or it donates the proton, and then you're producing, if you have an acid, you're producing hydronium ions, and it's actually measuring the strength of the hydronium ion that allows you to get the pH, okay, which is the power of the hydronium, or the strength of your acid. And we get a pH scale from 1 to 14. And that's what we're looking at next. So turns out that water actually ionizes without any influence. So a little bit of water dissociates to form, breaks apart to form hydronium ions and hydroxide ions. But pure water, the concentration of the products are the same. And so this Kw here is actually 1.0 times 10 to the minus 14. So that's a super small dissociation, so very, very little, right? So that means if we have products over reactants, right, and then this is a liquid, so it's not part of the equilibrium expression that we, in this particular case, we have the concentration of hydronium times the concentration of hydroxide gives you Kw. So if these are both 10 to the minus 7, 1 times 10 to the minus 7 times 1 times 10 to the minus 7 is 10 to the minus 14. And that's a number that I will provide you. This is going to be very useful. And so then the pH is calculated by taking the negative log of the H plus or hydronium ion concentration, which means to what power do I have to raise 10 to get to that concentration, right? So if the concentration is 1 times 10 to the minus 7, you have to 10 to the 7 minus 7 would be that concentration. That would have a pH equal to 7. And then if you had a hydronium ion concentration of 1.0 times 10 to the minus 4, the pH would be equal to 4. So that's also gives you the ballpark. And of course, if this number is not exactly 1, then you're not gonna have that relationship, but you can still estimate the pH. And so we get this pH scale based on this self-ionization of water. And so we have this equilibrium. As I said, the pH of pure water is 7, but then you can shift this equilibrium, right? So if you are dissolving a conjugate base, or if you're adding an acid to it, what will happen is, if you add hydrochloric acid to that, which means that's going to react with water to form more hydronium ion, right? So that's going to increase the concentration of hydronium, right? Which will cause a shift to the left, which will deplete the hydroxide ion concentration, and we're going to form more water, right, which becomes irrelevant, but that means now that we're going to have a larger concentration of hydronium, so your pH is going to drop to something less than 7. So a pH between 1 and 7 is an acidic solution, and if you do the opposite, if you add a source of hydroxide or something that produces hydroxide in solution, you're going to get a shift to the left also, but you are depleting then the hydronium ion concentration. Remember that if the Kw is equal to the concentration of H3O plus times the concentration of the hydroxide, and if this is equal to a constant, which is 1.0 times 10 to the minus 14, that means that if you're increasing this has to decrease, and vice versa, just so we can have that. But so if your concentration of hydronium is higher, then you have a pH smaller than 7. If your concentration of hydronium is smaller, then your pH is going to be larger than 7, and you end up with a pH scale that looks like this. And here are just some common household chemicals and things that you're familiar with, like citric acid, which is the acid in citrus fruits, has a pH of about 2, so that's pretty low. Phosphoric acid, which is in Coca-Cola. This is sulfuric acid, lead acid, and then Drano, we've already mentioned that is a lye, so you have more hydroxide there, and so you get this pH scale. Alright, so when we come back, we're going to do some really cool calculations and set up some wonderful ice tables.